Thank you for attending today's SEL webinar. Before we start, I would like to bring a few items to your attention. This is an audio-only broadcast. All participants are muted. Today's webinar will be 75 minutes long, including questions at the end of the presentation. There will be a recording, which will be available on our website as soon as possible. If you have any questions throughout the presentation, please submit them to all panelists with the Q&A tool at the bottom right-hand corner. Any questions that are not addressed during the live event and the Q&A session will be answered by our experts personally via email. Our presenters today are Andrea Di Tommaso and Zaza Saralidze from SEL. Andrea joined SEL in 2019. He worked on protection and control schemes, substation and power plant automation system before joining SEL. At SEL, he provides support on protection solutions to European customers. Zaza joined SEL as a protection application engineer in 2018. His main areas of focus are protection and control applications in transmission and distribution networks, traveling wave protection and fault location, remedial action scheme, and smart grid technologies. During today's webinar, we will discuss protective relaying for wildfire mitigation. I will pass the microphone to Andrea.
Good day and welcome to this webinar on protection relay for wildfire mitigation. Let's have a look to the today's agenda for this first part of the webinar. One of the main causes of wildfire is the contact of an energized conductor with the ground. So the today agenda for the first part is going to analyze the causes of a broken conductor. We will see the sequence of events, and we present here two methods for detecting a broken conductor. We propose a new algorithm for a fast detection and a phase discontinuity detection algorithm. We also introduce the incipient cable fault detection logic. This logic is intended to prevent fault in the cable that normally appears in cable splices, like in passage from an overhead line to a cable section. Broken conductor detection logic. The broken conductor detection logic monitors overhead lines in transmission and subtransmission. It is designed to detect a broken conductor before it converts to a shunt fault or a single conductor type of line. This is available as a firmware option already in our 751 device. This logic is based on the charging current analysis, as we will see in the next slides. The speed of the function may be used to block auto-reclose attempts, and this will help to mitigate possible hazards. Why conductor breaks? We can divide the cause into categories: defects and aging. This is one of the reasons for a conductor to break. This can be as a corrosion, as fatigue, and fritting. Last, other reason can be for localized damage, like power arcs, lightning strikes, hardware abrasions, gunshots, fires, and tree strikes. Let's have a look to the sequence of events that characterize an event of a broken conductor. We start to take as model an overhead line that is carrying a load current. The local and remote protection and circuit breaker. In the moment the physical break of the conductor, an arc is initiated between the broken segments. As the distance increases during the falling of the conductor, the arc is extinguished. At the end, there are two possible scenarios. First, one conductor is hindering from the tower, as we can see on the right side. Other case, the conductor hits the ground. In this case, the protection, for example, the one on the right side, can detect the ground floor and can perform a relay trips by opening the circuit breaker and temporarily clearing the fault. If the auto reclose function is enabled, it can reclose on a permanent fault. And that can generate hazard for the environment. A traditional method to detect a broken conductor is the I2 over I1 ratio. This method presents some challenges. The broken conductor can be in the grid as well as the protected line. And also, the results are not unique to a broken conductor. Inverse sequence current are present on all unbalanced faults. So, consequently, the function has to be delayed in terms of a second. A normal delay time often used is in a range of 5 to 60 seconds. The simple ratio between the inverse and the direct current cannot determine the direction of the broken conductor. To overcome all this challenge, SEL proposed one of the few single-ended methods with the use of a charging current. This is exclusive and patented by SEL, and will be soon available in the SEL 411L-1 and SEL 411-2, but is already available in the SEL 751. Let's go and see how it works, the algorithm. As mentioned, the algorithm will work with the line charging current. When the line is energized from the local end, as for example, the relay will measure the charging current. So, the first requirement for this algorithm to work is to define the minimum charging current that are required. The minimum charging current required is 50 and 10 milliamps, respectively for a 5 amps secondary side protection, secondary side CT, and 1 amps secondary side CT. This means, for example, that for a CT ratio of 400 to 5, 50 milliamps secondary will equals to 4 ampere primary charging current. A constraint we should have also with the voltage. The voltage must be greater than 33 kilovolts. And of course, the relationship between the currents and voltage that we will see is an angle displacement about 19 degrees. For example, between current EA and voltage VA. Go in detail on the algorithm. The algorithm uses 3 logic to define a broken conductor: a main logic, an alarming logic, and a low charging current logic. Let's see how it works with the main logic. So we define an horizontal blinder that corresponds to the minimum charging current of the line, or average charging current of the line. The first step consists in to phase current magnitude check. We will compare the magnitude of the phase current versus the minimum charging current. If the current stays below the minimum charging current, we will pass to the next step. and we will define a sector for a current angle check. A charging current should lie around 90-degree displacement with the water, so that we can define an operating sector for the function. In this case, that we check the phase angle current, we need to add a security check that it consists in a phase current incremental angle check. What we want to see is a change in the angle between its load condition that can lie in its reactive status to drop onto a charging current sector. In a loaded line, this will be available. So once we pass this third step, we go to evaluate the distance check for the broken conductor. It is a dedicated algorithm to check where the broken conductor happened. Once we did this check, and only if it is a single phase phenomena, we will generate a trip command. Coming back to step 3, in case of unloaded line, this algorithm can fail. In this case, we will not have enough change in the angle to be sure that there is a broken conductor. So what we are going to do is to go back to a traditional unbalanced check, a ratio between direct inverse and direct sequence current, and we will issue an alarm. The third logic consists for the low charging current. That can happen even in case of a loaded line when the broken conductor happens near the local or the remote bus. For example, a case of low charging current can be detected from the local bus once the broken conductor happens just after the circuit breaker. In this case, the logic will perform two steps. The first, it will check the status of the breaker and verify that all 3 ports are closed. The second step, it will apply current drop logic to detect if the current drops below the minimum charging current of the line. At this point, we have a torque control that is enabling or disabling the trip. That means that the user can choose, in this case, to issue a trip for a closing broken conductor or just give an alarm. How to set the broken conductor logic? First, we should enable the broken conductor detection in its main setting. After that, all the parameters that we need to define the broken conductor will be available to be set. The first is the line length, that is expressed without the unit. It can be in terms of kilometers or in miles. The broken conductor will issue a percentage of that number based on the broken conductor distance check. The second parameter is the broken conductor detection positive sequence line susceptance in millisiemens secondary side, or we can select a field measurement. Once we select field measurements, we will enable the BCCIM parameter that allow us to input the average phase charging currents, the term that we will use to compare the phase current, and that corresponds to the horizontal blinder seen before. With the distance check, we will define zones 1 and zone 2, where to trip in a base time or to use a delayed time for the broken conductor trip. The last 3 are the torque equation for the three logics. The first will allow broken conductor to a tree related to the main logic. The second is related to the broken conductor close-in or low charging current trip condition. 0 will just issue an alarm. 1 will allow the logic to issue a trip. The second is the broken conductor alarm logic. The last one is the broken conductor alarm logic. And that's the way we are going to define the fall location for the broken conductor condition. Once we pass the incremental angle check, that was step 3 of our main logics, we will check the distance by putting in relation the measured currents over the measured voltage and compare it to the ratio between the nominal current, nominal voltage, and our average charging current of the line that is expressed by the parameter VCCIM. This is times the total length of the line. Now, let's have an example with one field events. This is a 220 kilovolts broken conductor events that happen in a line of Transpower, New Zealand. The broken conductor here happens after 8 kilometers from the local line. That corresponds to a low charging events for the local end. Once we move to see the events from the remote end, we can analyze step by step what the remote end see. As first, as a pre-fault condition, we have the loading current that is flowing over the line. As soon as the broken conductor happens and the arc is initiated between the broken segment, we see a reduction of the current. More the conductors are distancing each other, more the current is reducing up to a point where the arc is extinguished. In that moment, we can see a breaking point for the arc. From here, we can evaluate the charging current that is seen from the remote end. And as we can verify, we jump from the loading angle to the 87.9 degree angle of this charging current. The algorithm and events are also present in our technical paper detecting and locating broken conductor faults on high voltage lines to prevent auto-recrossing onto permanent fault. It is possible to find in our website. Besides the broken conductor logic that will work as fast as no the traditional logic can do, we have also as a standard feature the phase discontinuity detection. That is the traditional element to define and detect open conductor. It can identify a broken conductor in case it results in an open flame condition for at least 8 cycles. And of course, it uses the unbalanced current as a criteria. So let's have a brief review of a broken conductor events. This is a sequence network for a single phase broken conductor, where we are ignoring the shunt capacitance of the line. If we use the current division rules, we can see that the ratio between the inverse sequence and the direct sequence is equal to the total sum of the direct sequence total impedance and the zero sequence total impedance and the zero total sequence impedance. If we can consider with an approximation that the total zero sequence impedance is 3 times the total direct sequence impedance, we can conclude that this ratio is close to 0.75. The phase discontinuity detection element basically consists in 3 logics. The first is an enabling logic that consists on the absence or loss of potential that is looking to any defect on the secondary sequence of the VT. The function has to be enabled, and we should have an energized line. That means a presence of voltage over the line. The second logic is the phase discontinuity unbalance detection logic that is using the ratio between the inverse sequence and the direct sequence compared to a settable threshold and a loaded line with a minimum load of 0.05 I nominal. Whether these two conditions are filled, we go to the last part, that is the phase discontinuity detection logic that is simply enabled by a torque control is going to detect which is the minimum phase current, as it takes it as an input, and in case it's phase A, it will declare a phase discontinuity detection element for phase A only. Same for phase B and for phase C. The way to say this function is simpler too. We just have to enable the function to define the torque control element that will enable the functions to work. That correspond normally to the absence of a phase over current elements, fold, and we are going to set a minimum threshold for the function to work. Typically, it's been seen that this ratio is higher than 0.15 for a single phase open events. So enabling the logic, define the torque control elements, and define the minimum threshold to be overcome. Let's go to the final and conclusive part of the first part of the webinar, that is the incident cable fault detector. The incident cable fault detector is used to detect a self-clearing half to one cycle over current events. This type of events are common in cable that can be as an enclosure, but it can be even in an outside environment, like pass from a hovering line to a cable section tower. Of course, it will work with detection current, means that it will use only currents and will be supervised by torque control and pick up and drop out talents, as we are going to see in the next slides. So here is the logic, and for sake of simplicity, we are going to consider an extreme simplified of self-clearing overcurrent event of a cycle. In this case, the absolute value of the current, of the raw current, will be used, and we will work with the samples rather than with magnitude and phase. This current, raw current, is compared to a threshold. In case 2 of samples are over this threshold, the timer T1 will trigger the second timer. That is the first condition for the enabling of the counter. This dropout time of 32 samples is used to avoid that the next half of a cycle is going to retrig the timer T2. And the 62 sample cycle is ensuring that for the next cycle, we are going to see and to check if this is a self-clearing half to one cycle events through the timer T3. This negator here is ensuring that after 32 samples, we have cleared the overcurrent events. These two timers together will trigger the timer T4. First, we trigger the timer T2. Second, we have the self-clearance of the overcurrent event. And third, we are going to trigger the timer T4 that will trigger our counters. This function will count events. So we are going to set one alarming threshold and one tripping threshold in terms of counted events. To set the function is simple as well. We have just defined one overcurrent threshold. It uses only currents and only one setting of current, both for a phase events than for a neutral current impulse. This is be adapted by the ratio of the two CT ratio, the phase CT ratio over the neutral or core balance CT ratio. Here, with the 50 ELC, we will set the counter threshold for alarming. And with the 50 ITRC, we are going to set the counter threshold for tripping. We have a torque control and we have a reset. It can be manually or can be to a SEL logic, use of SEL logic. In order to evaluate status of our cable splices online, we can go and check events for this incident cable fault function only. We have a log status for all events that the protection see for each phase, just issuing the command his 50 INC and press enter. We will see for each day and for each time the counting of events. This will help us to decide if we have to do some predictive maintenance and go and check the status of our lines passed to cable. So in our, for example, overheats to cable section junction. With this, I complete my first part of the webinar and I will pass the microphone to Zaza. Thanks.
Thank you everyone for participating in this webinar. The second part of the presentation, the objectives of the second part of the presentation will be following. This is traveling wave-based fault location, line monitoring function, and auto reclosure permissive or cancel operation. So all those three functions, which are listed here, quickly identify the fault location, which can help us to locate wildfire or prevent wildfire to happen. So I will go through each of the item and try to demonstrate how we can either prevent or locate fault quickly. So let's start. This slide will help us to imagine what traveling wave may look like in physical dimension. So this white rope here represents power line, and the man in the middle represents for example, fault on the line. So let's play the video. Okay, so if we saw here on the video, once the man hit the rope, the waves arrived on the both sides. So it were generated in the moment of the heating of the rope, and it was transmitted to the both sides. And then it was reflected from both sides and went back to the fault or disturbance place. So let me play once again so we can see it more clearly. Okay, so we see how waves are generating, how waves are transmitting to the both end and then reflecting to the point where it were generated. So very similarly, traveling waves are generated in transmission line or distribution line when sharp disturbances are happening. Let me grab the laser point. Sorry. So let's move to the next slide. So let's take the tower, so transmission line tower, and assume that we have 500 kV overhead line. So in case of 500 kV overhead line, phase to ground voltage, I mean the peak voltage of the sine wave. So if you calculate according to this formula, will be 408 kilowatts. So this will be just peak. Okay. So if short circuit is happening just on the top of the sine wave, so we have very sudden, sorry, just take me to the laser point here. Okay, so the sudden change of voltage is happening. So we have collapse in this case from 408 kilovolts to the near to zero. So this sudden change is causing a traveling wave to be generated. So we have here a single line diagram, and we have fault here. And once the fault is happening, let's assume that 408 kV was the peak voltage of the sine wave. So it generates the traveling wave current. So let's call it IF. So if we take this formula, Ohm's law, according to Ohm's law, so we have a fault current, we can calculate the fault current. So in this case, the impedance, we call it characteristic impedance for this particular line is 350, let's say. So we can calculate the current. As we see here, the waves are generated. The voltage wave and the current wave have same polarity, and the same is on the left side. It has same polarity. So once it's generated, so voltage and currents will have the same polarity. Okay. So the wave more looks like this shape. And once it is generated, let's talk about the current waves. Once it's generated, it will be transmitted to the nearest substation. So the substation PS and substation PR. Okay, now let's talk about the velocity of the wave and how it can help us to identify precisely fault location. Okay, this is electromagnetic phenomena, traveling wave, and of course, we know the velocity of the electromagnetic wave is the speed of light and 300 kilometers per millisecond. So if fault, in this case, is happening 1/4 of from substation A and 3/4 of from substation B, then we can estimate that the first wave of traveling wave will arrive in substation A in 0.25 millisecond and the second wave in substation B, the first wave for substation B will arrive in 0.75 millisecond. So knowing a first arrival time will help us to identify where the fault is. Let's say if fault is right in the middle, then arrival time for first wave will be identical. It means that we have fault in the middle, and so on. So knowing those arrival time will help us identify the precise location of the fault. Okay. So normally we are calculating or we are measuring traveling wave line propagation time. So line can be shorter or longer than this line, and we can measure it by just energizing a line from one end, and we can measure the line propagation time. So this is easy to measure by just energizing the line. Okay, so in this slide we see a so-called Bewley lattice diagram. So this diagram is helping us to do the manual analysis of the traveling wave records, for example. So how we can read or how we can do the analysis by using lattice diagram. So similarly to line length, here we have line length, but in vertical we have time axis. So when short circuit is happening, as we saw, first wave will arrive, of course, on left side, and on the faster, and the right side will arrive a bit slower, bit later. But we also have a reflection from that substation, which will go back to the fault location, and fault location will reflect that wave again. And the same is happening for right side of the substation. And we may have this kind of reflections, so it will not continue infinitely, but we can see first arrival, of course, and the next few reflections. So knowing and having this tool and do the analysis, we can verify our fault location by just manually. So we can open the software and verify the fault location, what our protection device gave us. So, but we have to be conscious about reflection from other substations. So we may have some reflections from other substations as well. So we need to consider those as well. So this is how Bewley lattice diagram analysis may look like. So from left side, we see the record from the left side of the relay and from the right side of the relay. So we see the records. We can open those two records simultaneously in one software and do the analysis by manual analysis. So yeah. So what we see here on the left side is first arrival. This will be, of course, this will have a larger amplitude, and the right side also will have a larger amplitude. And the next waves, what we see here, those are reflections from the fault. You see, the first reflection and the second reflection, and the other reflections are not easy to see here. But the same is here, the first arrival wave and the next arrival and the next arrival, and then it's attenuation. Okay, so in this way we can manually do the analysis, but before the manual analysis, the SEL T400L or SEL T401L, those two devices which can do the traveling wave fault location, also for SEL 411, but let's focus on these two devices, can automatically calculate the fault location based on the first arrival time and give the result. So it is immediately. So we are getting results immediately, but later we can verify our results by using the Bewley lattice diagram. So how this can help us to prevent or identify the faults or identify the location of the wildfire. Of course, knowing the exact location. So what is the precision of this function is about 300 meters, which is just one tower spine of the overhead line. So knowing very precisely fault location can give us very good advantage to prevent distributing wildfire. So this is very great tool for us to find the location and find the location of wildfire. Okay. So the next functionality which can help us to prevent wildfire is line monitoring function. So what line monitoring function does is that it monitors the traveling wave arrival, but with low energy traveling wave. It monitors the low energy traveling waves. So before the fault happens, so it often generates low energy waves, and our protection devices can detect those low energy waves. And if it is repeating, so let's assume that it is happening in short time of period twice or 3 times, so it is high likely that we may have a risk of having a fault in that particular location. So what our device is doing is that it is dividing line in short sections. We call it beans. It's 0.25 kilometers, so which is about 1 tower spine. So it divides and it counts the number of low energy events. So if it's surpassing the number of expected events, then it may generate alarm signal, or even we can generate a trip. So we can, before fault happen, we can generate tripping signal. Okay. So once again, let's summarize how line monitoring function can help us and what the benefits it gives us. So we can see the location where the vegetables are approaching the line or close to line, and we can do the encroachment of those and trim those vegetation and prevent faults, therefore prevent wildfires to be happen. And another thing is we can locate filing insulators, and so before the fault happens, so fall insulator can broke, but it may not cause the fault, but it will cause some low energy traveling waves. So we can find those kind of failures. Another thing is dirty insulators. So we can find those dirty insulators and do the prevention, so we can wash them. And some non-electrical events such as brush fires. So we see here the brush fire, if it happens brush fire, so for some other reasons, so it can ionize the air here, and it may trigger low energy traveling wave. So we can using a line monitoring function, we can even identify where the potential fire is happening right now. So those are four main items, the benefits of the line monitoring function. So with this record, so I can easily explain how line monitoring function can operate. So here we see voltage record. So this is sine wave and the traveling wave of the voltage. And the downside, we see the current. So this is definitely short circuit here because we see the current is very high. But interestingly, here we have some precursors. We call it precursors. You see here's very small, low energy processes are happening. So before the fault is happened, we see some phenomenon, some traveling waves are arriving. So having this information before fault happens, so it may happen the minutes or hours before, so we can seeing this low energy traveling wave, we can predict that fault may happen. So let's zoom in these two location and see what we have. So what we have here is same polarity here. This red dots, red line is from left side of the substation, and the blue one is on the right side. So as we remember, time between those two peaks determines the location of the fault. Okay, let me demonstrate. Okay, so knowing the time between those two peaks, so we can easily calculate where the fault may happen. Okay, this is the first precursor, and then now is the second precursor here. So we snap on the peaks and measure the time between. So it is the same 97 microsecond. Therefore, the disturbance is happening on the same location. So this diagram or this diagram is showing us how line monitoring is doing the calculation. So as I told you, that it is splitting line or dividing line by pins, 250 meter pins, and it is calculating how many events happened on each pin. If it is so alarming, like if it's surpassing some threshold, then we generating some alarm or even tripping. Okay, let's assume that we have several events. Okay, here we see it's like 7 events. Okay, and how it does the average, calculates where the exact location is. So here we have two neighboring beans, and it is just calculating where is the high likely to fall to be happen. So this is the bean number 10. So this may correspond to tower number 10 or 11. So we can easily know that, okay, tower number 10 may have problems. So we can go there and see what is happening. Okay, so we may have tapping online. So this is we see here overhead line has 2 taps. So why tapping is so important? If we have tapping and we have switching devices there, most likely it's a circuit breaker. And when circuit breaker is opening or it's closing, the same for the second, same is for second tap, it generates traveling waves. So we have to treat this tapping point differently. So we may have many events generated in these 2 locations. So we have to either disregard those 2 locations or have different location for that. So let's say for these 2 locations, we have daily counts with automatic reset at midnight. So it resets every day, each day. But for other parts of the line, it stays. So it is like accumulating. And of course, we can reset it manually, but normally it's just accumulating. And if number is higher than in one location than compared to others, then of course this particular location needs to be checked. So what type of information is available and how we can use line monitoring function? The first and important is alarm word beats. So we can use those alarm word beats, for example, to generate some contact information. So it can send some information to the operator in this way, or even send the information via DNP3 protocol. Or we can, by taping the command LIMO, we can get the information. This is much more, this contains much more information, such as statistical information inside the relay, how many started events we had in which beans and so on. So the files can be represented, can be downloaded and represented in text file as well. So, and we can use integrated HMI for testing purposes. Line monitoring function, so it's simply to use. So we don't need any external software to use this function. And it works, of course, over direct fiber or different kind of multiplexing communication. Okay. So it monitors and alarms on low energy events, as I already explained. And it has separate alarms for line taps. So we don't mix the line tap generated signal and the other type of signals. Okay, another great function for preventing wildfire is outer enclosure control by fault location. So it says by itself that once we know the high risk of wildfire, we may cancel the outer enclosure function. So This function also can be used, of course, for hybrid lines, which means that for underground cable or submarine cable, we can cancel the outer reclosure function. So, and what I mentioned, just we can cancel outer reclosure where is the higher risk of having wildfire. So if we have short circuit on those areas, those sections, so we just cancel the outer reclosure and lower the risk of having wildfire. So of course we can use the same approach for public safety concerns where the line is crossing some specific area where is the high risk of having injury, and we can cancel the outer reclosure as well. Lines with sections having low success rate. So we may have some section of the line where is the low success rate. Having outer reclosure, we can cancel in these cases as well. So this one is just a single line diagram for hybrid overhead line, but in this case we have underground cable, but this can be different sections such as high risk of wildfire or different high risk of locations there, and we can just identify those locations and block the outer reclosure. So why we are pointing this function, why we are using this function here, we are using because we have very high accuracy of the fault location. That's why we can very precisely identify the section of the line and do the blocking of the outer reclosure. Here is the logic, how it works. So we may have different sections, more than one sections, where we can have a blocking of outer reclosure. So as a conclusion, I would like to repeat again. So what we have double and single-ended traveling wave fault location methods, which is accurate up to 300 meter, so on tower spine. Line monitoring function allows us to prevent risk of faults and wildfires. So line faults history allows us refining traveling wave faults. So having a history from either from traveling wave fault locations or line monitoring functions, we can do the statistic, or we can do the refining of traveling wave results by adjusting traveling wave time, propagation time. So traveling wave fault locators working in real time enables adaptive location depends outer reclosing, which can be used to prevent high risk of wildfire. So using all these listed functions, we can locate or prevent having risk of wildfire. So this is the last slide. Thank you everyone for attending and listening to me. If you have questions, please ask.
Thank you, Zaza. Thank you, Andrea. Now we have arrived at the Q&A portion of the event. As mentioned before, if you have any questions, please submit them to a Q&A section on your right-hand corner. Our panelist today is Zafer Kormkas. Zafer is a senior application engineer at SEL who works with the company since 2013. Our panelists and presenters now will take any questions you might have. The first question that we have is, how does the current drop logic decides it is not a sudden drop load?
So, okay, I'm gonna answer to this. It's the first part of the webinar. So, this is related to a low charging current piece of the broken conductor logic. So the logic will look to the magnitude of the current and is going to check if it is lower than the charging current of the line and now perform the angle check for the low content of the current. But if it is a single phase phenomena, it will allow the user to decide whether to issue a trip or give it just an alarm. Hope it can.
Thank you, Andrea. Another question, how the broken conductor method compared to the traveling wave-based method?
Okay, again, so as we saw in the last part of the webinar, the traveling wave is based on changing on voltage. So this is the key point to make a traveling wave methods to work. When you have a broken conductor, let's say, unless the conductor is not going to hit the grounds, the only change on voltage can be the reduction of the load, the loss of the load on that phase. So in this case, the traveling wave is challenged by the broken conductor event. The broken conductor logic will be the suitable one to be used to detect the phenomena. Okay.
All right. How can we control the auto reclose function if it is implemented in an external protection device?
Okay, I will answer on this question. So SEL T400 or 401L has free programmable output contacts, which allows us to control external circuit of the reclosure. So it can be easily interconnected.
Thank you, Zaza. One more question. How would you compare the broken conductor versus phase discontinuity detection?
Okay. Just the broken conductor is, as showed, is going to use a line charging current of the, while the phase discontinuity detector is based only on the classical ratio between the inverse sequence to the direct sequence current. And as we saw, this method is not suitable to detect a fast trip, to perform a fast trip of the circuit breaker, since it needs to be coordinated for a long tripping time, like in order of a second, 5 to 60 seconds.
Thank you. Another question. In how many sections we can divide for non-homogeneous line for traveling wave fault location settings?
Okay, we can apply up to 5 different sections. So it allows us to divide line up to 5 sections, and the setting for each section, traveling wave propagation time, can be set differently.
Thank you. We hope you have enjoyed today's SEL webinar. To learn more about this topic, please visit our website. If you would like to connect with our presenters or a local SEL expert for follow-up, please take a moment to indicate this on the form that will appear when exiting the event. Again, a recording of this presentation will be available as soon as possible. Have a wonderful day.